Good morning to everyone. Welcome to the session of Computer Architecture. Myself R. Narendran, working as Assistant Professor in Erode Sengundar Engineering College, Tudupadi. So coming to the basic properties of computer architecture, we have already seen in the basics. So what is computer architecture? So before entering into the session, we shall have a close gist of what is computer architecture. So the hardware and software components are united together in a computer. So how effectively they are working together and how effectively they are correlated together to form a basic operational concepts. So that forms the basics of this particular session. Okay. So coming to this session, this is all about basic operational concepts in computer architecture. Okay, so to perform any given task in an appropriate time or duration, a program is needed. So what is a program? A program is a group or collection of codings, so which makes way for computer to work in a proper way. The program consists of list of instructions. These instructions act as a instruction that are given to the computer to store in the memory to perform a particular task. So the individual instructions are brought together from the memory into a particular processor, which can able to execute the specific operations. These operations can be of anything. For example, the operation can be of normal arithmetic operation or logical or any kind of bitwise operations. So any kind of operations can be carried out in this particular operational concepts. So the data must be stored and the stored data should be retrieved from that particular memory location. So this is the basics about the operational concepts. So for performing these kind of operational concepts, we have to segregate those kind of instructions into a separate one. First, the instruction is fetched into the memory and then into the processor. Okay, so the operand at a particular location, for example, I have specified here by mnemonics notation as LOCA. So these particular operands are fetched and added into the content of R0. R0 is nothing but the register. Okay, R0, R1, R2 are some kind of general purpose registers. They are used for storing and retrieving a particular type of data into the memory. So finally, the result of a particular data is stored in the particular register that we are specifying. Okay, here R0 is the register name that I have given. Okay, so consider this particular diagram. So it is a connection between the processor and the memory. So how the processor, that is the central processing unit, is correlating with the memory unit. Okay, this is a main diagram behind the computational task. Okay, so this specifies different kinds of registers and different kinds of memories. So first of all, we are seeing the concept called as main memory. So it is the CPU memory. So it forms the first part of any kind of memory. So next one is MAR. So memory address register. So PC is the program counter and IR is the instruction register. So these are all present in the CPU only, that is central processing unit. So by using these different kinds of register memories only, we can able to do the bit by bit allocation of different types of computations. Okay, so next one is MDR. So memory data register. So MDR is nothing but memory data register. In this register, so the data is processed. So next one is R0, R1, R2 followed by Rn-1. This is nothing but a general purpose register. So by using these general purpose registers, we can able to process bit by bit allocation of memory or bit by bit storage of a memory space or bit by bit retrieval of a particular data from a huge set of memory space from the CPU. So next one is the control unit and the memory, arithmetic and logical unit. So MAR, PC, instruction register, MDR, R0, R1, R2 up to etc. These kind of general purpose registers, and control unit and arithmetic and logic unit. These are all mainly needed for interacting with the processor in terms of computation of different kinds of memory spaces. Okay, so this particular diagram is mainly meant for how the different types of data transmissions and address transmissions are carried out between the processor and the memory space. So memory can be of any kind of memory, not only the main memory. Okay, so here are the basic gist of what are the different types of registers that we have mentioned in that particular diagram. So the instruction register. So instruction register is nothing but it's a special kind of register that is used to hold the instruction that is currently being executed in a particular memory space. Okay, so there are many kinds of instructions that are being thoroughly given to a particular central processing unit. So in that, this particular instruction register plays a vital role in holding the instructions that are currently being executed. So next one is program counter. This program counter is nothing but it is a specialized kind of register that keeps track of execution of a program. That in simple words we can say that the program counter stores the next instruction to be executed. Suppose the instruction register is processing a particular type of data or holding a particular type of instruction that is currently being running, whereas the program counter will take care of the next instruction that is being executed in the next step. So these two are different types of registers. Okay, so next one is in order to process the better way of communication between the data and address and the control signals, we are going to make the different kinds of movement of communication by means of different kinds of registers. For example, MAR, MDR, we can consider this. So MAR is nothing but memory address register. So it is particularly meant for holding the address location that is to be accessed. Okay, so in the name itself it is specifying as MAR, that is memory address register. So it holds the address location that is to be accessed, whereas MDR is the memory data register. So in the name itself we can able to identify that it is particularly dealing with data. So the data can be of anything. It can be of image or it can be of any bit by bit allocation of data. So it will consider it as a data. So it contains the data that is to be written or that is to be read out from the particular address location. So that forms the part of MDR. So get clear with this. So first one is MAR. It is used for memory address register. So it is used for allocation or holding of address location of a particular data to be accessed. Whereas MDR is nothing but it contains the data that is to be written or that is to be retrieved or that is to be read out from the address location we are specifying. Okay, so next. So these two forms of registers are very useful in retrieving and writing of a particular data. Okay, so we are having different types of registers. Okay, so how these particular communication or connection is carried out between the processor and memory, we have to go through a set of instruction steps. Okay, so first one is the program will be in the memory in a particular device. So the instruction register will take care of the current instruction which is particularly in the movement. Okay, for example, I have initiated a particular type of mnemonic data. So in that particular case, the particular first instruction when it is being executed, it will be stored in the instruction register IR. Okay, so the next one, the next instruction, the second instruction to be executed will be saved in program counter. Okay, so the content of the program counter is then transferred to another kind of register called as memory address register. So we have already carried out two types of registers, memory address and memory data register. So in this particular type of register, we are dealing with the content of program counter that is to be transferred to memory address register. The read signal is sent to the memory. So and the first instruction is read out and the particular data will be stored into memory data register. So we are holding a particular data after particular instruction is being carried out, right? So so that particular data should be stored in memory address register. We are specifying it as MDR. So next, the content of the memory data register is to be transferred to instruction register, because next instruction is going to be processed, right? So next instruction is processed by program counter, whereas the current instruction is carried out by instruction register. So afterwards, these type of loopings will be carried out throughout the whole set of instructions are being executed. So afterwards, we are going to decode and execute that particular instruction. Okay, so for that purpose, we are having a additional type of data called as, register called as general purpose registers. Okay, so general purpose registers are nothing but we are naming it as R0, R1, R2 up to etc. we will be specifying. So these are generally used for basic storage and retrieval of data. Okay, so for efficient storage and retrieval, we are using general purpose register. So afterwards, this processed data will be stored in the arithmetic and logical unit. It will deal with whether the instruction we are going to process is arithmetic or logic. Okay, so based on that, it will store the result back into the memory. So once this particular cycle is being executed, the next instruction will be executed simultaneously in the looping way. So next, the same set of instructions will be carried out, and the program counter will increment the particular next type of instruction, and the next instruction will go on until we are going to finish that particular data. Okay, so here is the set of operational steps that we are specifying. So first one is the the program resides in a particular memory. The program counter points to the particular instruction, first instruction. Okay, so next one is the program counter content is transferred to MAR, that is memory address register. Next, the read signal or write signal is then being transferred and it is sent to the memory unit. So the read or write signal is then processed and loaded into which memory? So memory data register, that is MDR. Okay, this kind of register. Next, the content of MDR. So we are to process that particular content, right? So that content of MDR is then transferred to instruction register. So we already know that instruction register is nothing but it holds the current instruction being executed. Okay, so next one is we are getting the opcode of a particular ALU. Okay, so for particular ALU being executed, that is ALU is arithmetic and logical unit. It will process which kind of data that is to be executed. Okay, which kind of operation it should perform, whether it is addition, subtraction, multiplication, movement of data, or some kind of data communication instruction or signal. So next, the result will be stored, and when the particular set of instructions gets completed, it will point to the end of statement, EOF. Otherwise, it will move on to the program counter. The program counter checks whether next instruction is there or not. So if some next instruction is there, then the program counter will process the above set of steps continuously for next instructions. Okay, so up to this we have dealt with the connections between different types of process, that is connection between different types of registers in correlation with the processor and the main memory. Okay, so this is what all about the basic operational concepts that is being carried out in a particular computer architectural way. Okay, so additionally we have to see the one more point at finally. Okay, that is called as interrupt. So interrupt is a main thing behind every instruction to be executed. You have to notice that. For example, the normal execution of a program may be preempted. Suppose if some devices are in rush up of some task to be completed. For example, a normal process is going on. Suppose I have to interrupt that process to execute a more important and quicker way of another instruction that is to be executed at once. Okay, for example, I am going to process a particular data. Meanwhile, I am in need of printing a particular 10 pages. So I will stop that particular process and then I will move on to next process that is called as I have to take the printout of 10 sheets or something. Okay, so meanwhile if I am taking that printout, I just make the current execution of instruction to be subtle. For example, I will make it to wait for a particular period of time until I complete the next task. Okay, so that is the normal execution of a current program must be interrupted. The devices arises a signal. That signal is called as interrupt. So there are different types of interrupts are there: interrupt 0, 1, 2, 3 up to etc., which specifies hardware interrupts, software interrupts, any kind of interrupts. Okay, so for handling these kind of interrupts, we are having a special kind of routine called as interrupt service routine. Okay, so the current system information backup or restore. Okay, so for this purpose also we are using interrupt as a signal. So interrupt is nothing but a process that is being interrupted, or that is being made to wait for a particular period of time until another important task needs to be completed. Okay, so in this class we have discussed the basic operational concepts and different types of registers and different types of communication that is handled between the processor and the memory. Okay, so we will see with the continuation of interrupt in the next class. Okay, until that, thank you for listening. We will see in the next session. Thank you. Welcome to the session of computer architecture. So today is the second session, and in this session we are going to see the system buses. So myself R. Narendran from Erode Sengundar Engineering College, working as an assistant professor in the Department of Information Technology. Okay. With no further delay, we shall move on to the concept of system buses. Okay. So first of all, what is system buses? So system bus is one which plays a main role in the data communication. A bus is a communication system that transfers data between the system components such as computer and other peripheral devices, or in fact in between two different computers also, that is among the different networks. A system bus is a single computer bus that connects major components of the computer system, combining the functions of the data bus, address bus, and control bus. Basically, there are three types of buses as we know. So the data bus is the bus which involves the transfer of data from one particular part of a computer component to another particular part of a computer component, or from one computer component to some other computer component, which forms different network. A system bus is a whole bus which involves data, address, and control informations. So the address bus is used to determine where the data is stored and where the particular data is retrieved. Okay, so these forms the system buses. So next one is the control bus. The control bus involves the transfer of data, uh, that is the transfer of control information such as read, write, update, and such kind of operations from one particular part of a computer to another particular part of a computer. Okay, so this forms the main um, reason behind why we are using system buses and what are the significance of system bus. Okay, so hope you are clear with this particular concept. Okay, so next we will move on to the types of buses. As I have already told you, there are different types of buses such as the data bus, address bus, control bus, and in fact power buses and external buses also. The address bus is the one which carries memory addresses from one processor, that is one CPU, to another components of the CPU. For example, from one processor to some other primary storage and input output devices. Okay, so next one is data bus. Data bus is the one
which carries the data between the processor and some other components of the computer. Okay, so next one is control bus. The control bus is one which transfers the control signals, electrical pulses, such as control signals, for example, read, write, and this kind of control signals to different parts of the computer. So another one is external bus. The external bus is the cable which is used to connect between the internal devices of the computer to the external devices. For example, peripheral devices. We can know different types of peripheral devices such as a printer, joystick, mouse, a keyboard, and some other kinds of external peripheral devices. So these peripheral devices get communicated with the computer by using bus, which is called as external bus. Okay, they are also used to connect internal buses and also internal devices. Okay, so this is one of the important aspect. So what are the functions of buses? Okay. So meanwhile, we should know what are the different functions of buses. So basically, we know that buses are used for data communication. That is communication from one part of a system to another part of a system. So this communication involves various types of data transfers. For example, data sharing. All types of buses found in the computer transfers the data between one peripheral devices to another peripheral device, or one peripheral devices to internal parts of a certain components of a computer. So next one is addressing. Okay, so the direct example is address bus. So addressing, a bus has address lines. As we know that microprocessors are having address lines, which we can specify it as AD0, AD1 up to etc. Will move on. Okay, in terms of powers of 2. Okay, so likewise, the bus has the address lines which match those of the processor. Okay, so this allows the data to send to and from the specific type of memory locations or address locations. Okay, while we are using registers, there are specific kinds of registers called as indirect and direct addressing. Okay, we will specify within square bracket, we will specify the content of the particular register by means of location. So this is some of the example of this address bus. Okay. Next one is power. So a bus supplies power to the some other computers. For example, the bus is nothing but a cable, that is a group of lines, right? So with the help of that only we can able to give proper power to the system or some other peripheral devices. So next one is timing. So the bus provides a system clock signal. So this is nothing but a control bus. Okay, so system clock signal to synchronize the peripheral devices attached to it with the rest of the computer components. Okay, so that is one of the important thing. So next one, so this is the basic architecture of system bus. So in this architecture, you can able to see the three different types of buses, such as control bus, address bus, and data bus. These three buses are communicated with CPU, memory, and input and output devices. For example, peripheral devices. So these you can see that control, address, and data bus is cumulatively represented by a dotted line. So these three buses, for example, control, address, and data bus, these three buses forms part of system bus. We can say these three in group as system bus. Okay, so that is one of the architectural diagram we have seen. So this is nothing but the bottom of the motherboard. So where different ICs and some other different components are connected. So you can see the red colored line. Okay, here you can see the red colored line. So this is nothing but the system bus. Okay, this is nothing but a system bus. So in the system, the buses in the motherboard, we can specify, we can see the uh, bus as here. Okay, so the diagrams and pictures shows the different types of buses. Okay, internal bus, external bus, and ordinary cable. Okay, so external buses are nothing but it forms part of the computer which connects the some other components of the peripheral devices. Okay, we can connect internal components of a computer to the external peripheral devices or components. Various types of buses are there. We'll see one by one in the upcoming slides. Okay, so SATA. So we can collectively say it as serial ATA. Okay, it is abbreviated as serial AT attachment. Okay, so the bus interface that connects the host bus adapter to mass storage devices such as hardware drives, optical drives such as CDs, and storage devices, and solid state drives. So you can easily see this once you dismantle the cabinet of the CPU. Okay, this is one of the data cable which is used for serial data transmission. There are two different types of data transmission: serial transmission and parallel data transmission. So this is serial data transmission. Next one is PCI bus. So it is nothing but peripheral component interconnect bus. Okay, so it connects the CPU and the expansion ports such as modem, NIC card, network interface card, we can say, and animation card and sound cards. So these are some of the external components. We need to connect these components with the processor or CPU, which are attached to the motherboard. So for that purpose, we are using peripheral component interface bus, PCI bus. So you can see in the diagram that the CPU is connected with the PCI bridge. Okay, so by using the PCI bus, the bus master and the DMA controller, that is direct memory access controller, gives the way for connecting the PCI buses with the CPU through PCI bridge. Okay, in the diagram you can see the four different white color strips. So they are nothing but these are the components wherein you can able to plug in or plug out the PCI buses. Okay, so this is nothing but a PCI bus, PCI bus slots. Okay, next one is AGP, accelerated graphics port. Okay, it is nothing but it is nothing but a direct connection between the card, graphics card, and this memory. AGP interface provides a dedicated specified bus for graphics data or animation data. So AGP cards are able to render the graphics as it is generally meant for graphics rendering, graphics card, or I can specify it as animation card. So there is a slot where you can see by means of red color marking. So there you can see AGP connector bus. Okay, so this is nothing but AGP connector bus. Next one is ISA, Industry Standard Architecture Bus. It is a standard bus architecture for data transmission or address transmission. It was first initiated by IBM International Business Machine for its own computer components. So it is a standard bus used for IBM compatible machines. Okay, so so these are all the different types of buses as of now we have seen. Okay, a quick review. I would like to tell you that so buses are something that is used to connect for the means of communication, which communication may be data transfer, address transfer, or control signal transfer, or power supply also. Okay, so next one is there are different types of buses such as internal bus and external bus. So these types of buses are mainly meant for data communication. So they are used for data sharing, address sharing, and control sharing, power supply production, sorry, power supply giving, and timing signal monitoring. So these three different types of buses forms a specified name as system bus. So we have seen these three: SATA, PCI bus, AGP, okay, and ISA. So these are all the basic things you need to understand while you are dealing with um, what is meant by bus architecture. So in this session, we have seen the different types of um, bus transmission, bus architecture. So what are all the features of buses, and this in this next session or in the next upcoming video we shall see the various types of arithmetic operations performed in computer architecture. Hope you like this video. So see you in our next video of this lecture series. Until then, thank you for watching. Good morning all. Welcome to the session of computer architecture. So, with the series of computer architecture, we are going to see in this session the concept of cache memory. So, in cache memory, we are going to see the various problematic and performance oriented topics in this particular session. This session will be able to give you a quick overview of what is cache memory and its performance oriented concepts, and followed by the various cache memory oriented problematic topics. Okay, myself R Narendran, working as assistant professor in the Department of Information Technology in Erode Sengundar Engineering College. With no further delay, we shall move on to the session of cache memory in computer architecture. Okay, so we have already seen about what is meant by cache memory in the previous concepts. So, what is cache memory? Let us have a quick overview of what is cache memory. So cache memory is something which is the most fastest memory that a particular system will have, computer will have. So whenever a particular request for a particular resource is going to main memory, the main memory will ask the cache memory which is associated with it whether it is the that is the particular requested file is there in the cache memory. Okay, so in that particular sense, cache memory is so much related to the fastest access of data in terms of memory management hierarchy. Okay, so let us have a look at what are the cache memory basic terms in terms of performance. Okay, so first one is cache hit, second one is cache miss. Okay, if the processor finds the memory location in the cache memory, a cache hit has occurred. Suppose I am going to search and ask or request a processor to find a particular file, whether it is present in the system or not. So whenever we are asking like this, the request will first go to the main memory. Okay, the processor will search whether it is present in the main memory or not. Suppose if it is not present in the main memory, so it will ask the cache memory. So the cache memory will find whether the particular data is present in itself or not. Suppose the um, memory location of that particular requested file is present inside the cache, then it is considered as cache hit. Suppose if the processor does not find the memory location within the cache memory, a cache miss is occurred. Okay, in the case of cache hit, the processor immediately reads or it can able to write the data in the cache file. Okay, so the cache memory basic things involves very important constraints. Okay, next, cache performance. So, okay, so two measures that categorize the performance of the cache are cache hit ratio and the effective access time, EAT. Okay, effective access time. The hit rate or the hit ratio is the total number of times referenced word or in the cache to the total number of memory accesses needed to access that particular cache. Whereas effective access time is the total number of hits into time per hit followed by the sum of total number of misses and time per misses. The total divided by total number of memory accesses needed for catch hit and catch miss. That is called as effective access time. So access time is common, right? So it needs to have a correlation between catch hit numbers and catch miss numbers also. Okay, I again read out a hit ratio is equal to number of times referenced words are in the cache to the total number of memory accesses. Whereas effective access time is the ratio between total number of hits and time per hits, and it's sum with total number of misses and time per misses to the total number of memory accesses. Okay, so let us have a look at some of the um, problematic sums. Okay, so a RAM chip has a capacity of 1024, that is 1024 words of 8 bits data, each having 1k into 8 sectors. The number of 2 to 4 decoder with enable line EL, okay, EN, okay, to construct a 16 into 16 RAM from 1 into 8 RAM is. Okay, so what is the thing they have asked? They have given the capacity of 1024 words of each having 8 sectors. The number of 2 by 4 decoders needed to construct 16 by 16 RAM from 1 by 8 RAM is. So we have to construct 2 by 4 decoder. So for that, so how much number of 2 by 4 decoders are needed for constructing this particular 16 into 16 RAM? So that is what they have asked. The I will read out the concept. So so a decoder is a combination of circuits. That is a combination circuit that is having n input lines and maximum of 2 power n output lines. Okay, so that is the decoder. Input line can be one, but the output line is the multiples of so that is a power of 2. So RAM chip size is 1k into 8. Okay, that is 1024 words of 8 bit each. So RAM to construct is 16 to 16. So typical RAM will look like it will be having a chip selection 1 and chip selection 2 pins and read and write signal pins and 7-bit addresses starting from AD0 address data 0 to address data, yeah, that is AD7. So totally 0 to 7 8 bits. So and the output will be 8-bit data bus. Okay, so the secondary one is a 2 by 4 line decoder. In this, the input lines are two, that is A and B are the input, but the output lines are D0, D1, D2, D3. So the highest priority is D4, so that is D3, and the lowest priority input is D0. So it will convert two input lines to four output lines. So that is the decoder. So the solution for the given sum is number of chips required is 16 by 16 to the ratio of 1 is to 8, right? So when we divide, we will get a 16 by 2. So 16 chips vertically with each having two chips horizontally. Okay, so the available decoder is 2 by 4 decoder only. So to construct a 4 by 16 decoder, so hence we are having 4 plus 1 additional of 1, that is 5 decoders are required. So the answer is 5 decoders. So another one, an instruction is decoded when it is kept inside what part? Program counter, instruction register, accumulator, arithmetic logic unit. So which forms part of the instruction. Okay. So an instruction is decoded whenever it is kept inside instruction register, because the instruction register IR is the current register. Okay, so it forms part of CPU's control unit that holds the currently running process. Okay, suppose n number of instructions are taking place in a particular pipeline. So the instruction decoder's work is to find what is the currently running instruction in a particular sequence of instruction. Okay, so the best answer is an instruction is decoded when it is present inside instruction register. Okay, consider the third example. Okay, so in this example, what they are asking. So consider a memory system that takes 25 nanoseconds to service the access of a single 64-bit word. Okay, so the bandwidth of the processor memory interface will be how much uh, number of bytes per second. So the answers given are 320, 160, 640 and 180. So just analyze the question first. So we are having the memory system that is having 25 nanoseconds to service a particular 64-bit word. So what they are asking is what is the bandwidth of the processor memory? Okay, that is uh, mentioned in terms of megabytes per second. Okay, we'll look into the answer. So 1 byte we will consider as 16 bits. So 64 bits is equal to 8 bytes. So 8 bytes of data can be accessed in 25 seconds. That is what they have given. So in 1 second, the number of bytes accessed is equal to 8 divided by 25 into 10 power 9 bytes. That is 320 megabytes. So the answer will be 320 megabytes. Okay, these are all simple logics only. Okay, so that is for a particular processor to be accessed, that is the bandwidth of the processor memory is 320 megabytes per second in order to access a particular memory system that takes 25 seconds nanoseconds to service a 64-bit code. So next question. So assume that L1 catch, the primary catch. Okay, the L1 catch with a hit rate of 70 percentage and L2 catch with a local miss rate of 10 percentage. If there are 1000 memory accesses initiated by CPU, then the number of access that will find a hit in L2 catches. Okay, I'll put it in this way. So you are given a system, the system is having L1 catch and L2 catch. So primary and secondary catch. The primary catch is having the hit rate of 70%. The secondary catch is having local miss rate of 10 seconds. Hit rate is 70, miss rate is 10 for different catches L1 and L2. So if there are 1000 memory access that is initiated, in how much number of accesses that will find a hit in L2 catch? Because in L2 miss rate is given, in L1 hit rate is given. They are asking about hit rate of L2 catch. Okay, so the solution will be number of accesses that will find a hit in L2 catch. Okay, is equal to miss rate of L1 into hit rate of L2. Total divided by total number of memory accesses. So 30 percentage of 1000 instruction plus 90 percentage of 1000 instruction divided by 1000 instruction. So it will give you 2,70,000 divided by 1000. That is finally we will get the answer as 270. So the number of accesses that will find the hit in L2 catch is 270. So okay. Next, what is okay? We'll put it in this way. They are asking the x value in this. So what is x? We will see. The cache has a hit rate of 95% and hit time of 10 nanoseconds. The cache block size is 32 bytes and the word length of the processor is 16 bits. During a cache miss, it takes X nanoseconds to fetch the first word of the block and 5 nanoseconds for fetching each subsequent words. The average memory access time is 15 nanoseconds. Find the value of X. So, average memory access time AMAT is equal to hit time of L1 plus miss rate of L1 into miss penalty of L1. So miss penalty is time to fetch the block from memory. Suppose I am asking to fetch a block of data. What is the time taken to fetch that particular block of data from memory? That is called as miss penalty. So total number of words in block is equal to 32 by 2, which is giving you the answer as 16 words. So as each word is 2 bytes. Okay. So average memory access time is 15 nanoseconds. So 15 is equal to 10 plus 0.05 into miss penalty. So totally, finally, we will get the answer as 25 nanoseconds. So that is the um, average memory access time. Sorry, that is the value of X. Okay. Okay. So another question. So consider a directed map cache. So direct mapped cache with 64 blocks and a block size of 16 bytes. Each and every block size is 16 bytes. To what block number does the byte address 1206 map to? Okay, we are having 64 blocks. Each block size is 16 bytes. So in which block the address byte 1206 will be mapped? So our answers are it does not map 6, 11 and 54. Let us see the answer. So block size is equal to 16 bytes. So memory block number is equal to byte address divided by block size. So 1206 divided by 16, we will get 75.3 as an average. The total number, so the given byte address, that is 1206, is part of 75th block. Okay, approximately we can take. So cache block number is equal to memory block number modulus of number of blocks in memory, cache. So 75 modulus of 16, we will get average of 11. So the answer is 11. So the block number 11, 1206 address byte is mapped. So students, so in this session we have seen about the various concepts called as cache performance, cache memory basics, followed by different types of um, memory addresses and performance oriented concepts. Okay, so in the upcoming sessions we can discuss more about some of the arithmetic operations performed and algorithms that are used to make the operations better. Okay, so until that, thank you for listening. We will see in some other lecture video in the upcoming sessions. Thank you for listening. Thank you, one and all.
Welcome to the session of computer architecture. So this is a series of computer architecture. We have already discussed about the basic concepts in computer architecture starting from the unit 1. So today we are going to see about a specific topic in unit 2, which is called as Booth algorithm, that is Booth multiplication algorithm. So this is going to be presented by myself or Narendran from IT department. So moving on to the session. So today we are going to discuss about the following concepts. Firstly, we are going to have a brief introduction about what is Booth algorithm, followed by the history of Booth algorithm. So next,
what is the flow of Booth algorithm starting from initial point of view. Along with it, we are going to see about signed and unsigned multiplication techniques. With no further delay, we shall move on to the topic. So first of all, the main objective of today's topic is we have to get the knowledge on signed and unsigned multiplication. So to solve various problems of the signed and unsigned multiplication, we are using the Booth algorithm. So Booth algorithm, in the sense Booth multiplication algorithm, which has the following concepts that we will see. Firstly, what is Booth algorithm? So Booth algorithm is a normal algorithm which multiplies two signed integers or two unsigned integers along with the concept of 2's complement. We have already discussed about the 1's complement and the 2's complement in the previous videos. Just go and check with those videos. So this is a basic approach which uses fewer addition and subtraction concepts that are very much involved in the straightforward algorithm of using basic binary multiplication. Coming to the history, this algorithm was invented by Andrew Donald Booth in the year of 1950 while he was doing research on crystallography uh, in the London college, so Birkbeck College, Bloomsbury. So through those research project, he has introduced a new concept called Booth multiplication algorithm. As he was invented, he named his own name for this algorithmic procedure. So the following points are to be remembered while doing signed or unsigned multiplication. Okay. So firstly, we shall see unsigned multiplication by using Booth. Okay, firstly, we have to take two registers. Registers, we already know, it's a small storage device that can store 1 bit of data at a time. So these registers, we are naming it as Q and M. So secondly, we are going to load multiplicand and multiplier in these registers. For example, if we are going to multiply 4 and 5, then 4 is the multiplicand and 5 is the multiplier. We are just going to convert this 4 and 5 as binary numbers. Okay, so by converting it into binary numbers, we are going to place it in the registers Q and M. Next, we also need a third register, which is called as A. We just name it as an accumulator register. We already know what is the benefit of accumulator register. Whenever we are not mentioning any of the names of the register in person or in depth, then the default register assigned will be accumulator. This accumulator is initializing the initial value as 0 while we are dealing with Q and M. Okay, we also need a register to store carry bit resulting from addition. However, we can take one bit of register Q minus 1. This is very important point that we will see while dealing with the sample examples. Okay, so following that, we are in need of multiplicand. Yes, so we will name the multiplicand as M, and M is added to the register Q, and the result is stored in the register A, that is called as accumulator register. Then all the bits of A, Q and Q minus 1 are shifted to the right 1 bit using shift register. We will see the valuable implementation of shift register in this Booth multiplication algorithm. So depending upon the last bit of Q and a single bit of Q minus 1, the various arithmetic operations starting from addition and subtraction we will be performing. Okay, so these are all the possible arithmetic actions that are being performed when we deal with this a, q and m, and depending upon the value of q minus 1. Okay, so the four possible arithmetic actions will be 0 0 0 1 1 0 and 1 1. So in this 0 0 and 1 1 during 0 decimal point and during the 0 number and 1 1, that is 1 1 is the binary representation of the multiplicand. So during those two actions we don't perform any kind of arithmetic operation, while 0 1 and 1 0, at those cases when 0 1 is present in our unsigned multiplication process, we have to add the multiplicand to the left half of the final product, whereas 1 0 is contradiction, that is we have to subtract multiplicand from the left half of the product. Okay, so one more thing we need to understand is till now we have discussed about non-signed integers, that is unsigned integers. So now we are going to see about signed integers, that is when we are dealing with negative integers. Firstly, whenever we are going to deal with signed integers, okay, so in those cases we have to convert it into unsigned integer. Okay, for converting this signed, that is signed negative integer into positive integer, we use 2's complement. So then this 2's complement value will be loaded into the register. For example, so if we are having or if we are going to deal with minus 5, for example 3 into minus 5 or 2 into minus 5, so while those things we can't able to place the same value of minus 5, so for that we are going to convert the binary equivalent of minus 5 and that is the 2's complement of 5. Okay, firstly we will take the value of 5 0 1 1 1, so this is the binary value of 5. So we are having minus 5, so for converting this 5 into minus 5 we are going to first convert it into 1's complement, and after converting those 1's complement value we have to add 1 to make it as a 2's complement. So the final answer will be 1001, that is 1000 plus 1. So the resultant value of 2's complement we are getting is 1001. So this 1001 is the 2's complement of minus 5. Okay, so that we are going to process in our final addition or subtraction. While dealing with these kind of things, we will be having these four different types of possible addition. 1 plus 0, that we will get 1, and 1 plus 1 we will get 0 along with a carry bit of 1. 0 plus 1 and 0 plus 0, those things are normal. So 0 plus 1 is 1 and 0 plus 0 is 0. So the basic example we have represented here is so 111 followed by 11, that is 111 1 1. So this is the left hand of the product, and we are going to deal with 0 0 0 1 0. So those we have to follow. So while dealing with this, we are going to add to these both these values. We will get the final carry bit, that is 1 plus 0 1, 1 plus 1 0 with the carry 1, again 1 plus 1 0 with the carry 1, again 1 plus 1 0, again carry 1. So 1 plus 1 0 followed by carry 1. So this final carry will be dropped out. This is the basic procedure. We will be dropping the leftmost carry bit while dealing with signed integer multiplication. Okay, so during dealing with subtraction of binary values, just a second. During that stage, we will be having 1 minus 0 1, 1 minus 1 0, 0 minus 1 which is again 1 with the carry 1. During those carry bits, we will be just omitting those carry bits. 0 minus 0 is 0. So for example, we are dealing with the following example: 0 0 0 0 0, that is 5 zeros, which is the main thing of the product, and we are going to minus the multiplicand, minus 0 0 0 1 0. While dealing with 0 minus 0, we will get 0, and 0 minus 1, we will get 1, and carry bit will be generated. So this carry bit will be carried out until the end of the, that is the left half of the product. Finally, again one carry bit will be generated. Those carry bit we will be using is it as a Pantham Paro integer. Okay, so this is the main concept, that is the main flow of data, starting from assigning the values of a, q, m and counter. Okay, so just for Booth algorithm, we just get ready with the basic concepts. Now we are going to have a look at how this flow will be going on. So initially we will be assigning a as 0, that is accumulator with the initial value of 0. So next q minus 1. So okay, so this value will also be 0. So along with that, m and q we will be generating. Okay, so that those values will be given, that is m is the multiplicand and q is the multiplier. Okay, so next one is count. We have to add the count value, that is it acts as a counter for generating each and every iteration. Okay, so next we have to look into q naught value and q minus 1. Suppose when we are dealing with this q naught and q minus 1 value, if q naught value is equal to 1 0, then we will be moving on to assigning a tends to a minus multiplicand. Okay, suppose if the q naught value is equal to 0 1, then we will move on to a tends to a plus multiplicand, that is accumulator plus multiplicand. Suppose if the q naught value is equal to 1 or it is equal to 0, then we will just go on to the arithmetic shift register process, that is we will shift the values of a, q and q minus 1. Okay, okay, next one is we will until this, the first step will be solved. Okay, accomplished. So we will have to decrement the counter. So count is equal to count minus 1. So now again we have to check whether the count value is equal to 0 or not. If the count value is 0, then we can end the particular arithmetic operation. That is, we are reaching the end of the particular product. That is, we have, when the count value is equal to 0, then we will be reaching the final solution of the multiplication. Suppose it takes 2 or 3 more counter value decrements, so again the looping will be going on. If count value is not equal to 0, then it will start from the scratch itself, that is q naught, q minus 1, q naught value is equal to 1 0, and it will move on to a tends to a minus m, or q naught q minus 1 value is equal to 0 1, then it will tend to a tends to a plus m. Likewise it will be going on. Suppose if the q naught q minus 1 value is 1 1 or 0 0, again we will shift the register in the right side part, so that is a, q and q minus n will be shifted right, and the counter value will be decremented. Again the solution, again the loop will be going on until it reaches the end of the product. Now we will get a clear idea. So suppose the given multiplication sum is 7 into 3. Okay, this is a unsigned integer. We are dealing with unsigned integer of 7 and 3. Okay, so now we will assign a, q, m and q minus 1. Okay, so m is the multiplicand and q is the multiplier. Okay, so we will generally assign q as multiplier. So here we are having 7 and 3. So 7 is the multiplicand and 3 is the multiplier. Just listen carefully. 7 is the multiplicand, 7 is the multiplicand and 3 is the multiplier. So a multiplicand will be represented as m and multiplier will be represented as q. That's it. So we will have to count the bit values. Okay. So we m that is multiplier and q multiplicand, both bits are 4 bit digits. So we are going to make the accumulator as 0 0 0 0. That is how much digits are there in q and m. You have to assign those kind of bits, those number of bits to accumulator. Okay, so now we are going to process the proceeding steps. For example, okay, in the first cycle, okay, we are just referring those flowchart idea, and now we are moving on to the basic thing. So we will have to identify q naught value. So here, just a second. So q naught value and q minus 1 value we are going to check. So the q naught and q minus 1 value is equal to 1 0, means here also we are getting those values. So if both the values are 1 and 0, so then we will make the concept of a tends to a minus m. Okay, so after shifting these particular values, we are just moving on to the shift register. So we are just shifting right. Okay, and we can able to decrement the value. So after shifting, we will just do the next cycle. So in the next cycle, so it tends to 1 0. Q naught and q minus 1 value is 1 0. Whenever 1 0 is coming, we will be doing a tends to a plus m. This is the second cycle, and just we are going to decrement the value. Next cycle doesn't end. So we are just moving on to the next cycle. Here 0 1 is coming, so a tends to a minus m. After shifting, we are getting the value of a tends to a plus m because 1 0 is coming. So likewise, this process will be going on until we are getting count value as 0. Finally, during the shifting process of this shift register in the third cycle, that is we are doing a tends to a minus m in the third cycle. So the after third cycle, as we have initialized the value of a as 4, that is 4 zeros. So during the third cycle end, we will get the count value as 0. Now the count value is 0 and the final result is obtained as 1110 1011. Okay, so this is the final step of getting the final answer for 7 into 3 or 7 into minus 3. Just in these two examples, we have got clear answer as signed multiplication and also unsigned multiplication. In this slide, we are dealing with unsigned multiplication, and in this slide we are dealing with signed multiplication because 3 is a negative value. So we are going to just convert those 3 value. Okay, the binary equivalent of 3 is 0 0 1 1. So we are just going to take the 2's complement value of 0 0 1 1 and then just we are going to use those 2's complement value in this particular procedure. So there is only two, just a recap, we are just dealing with 4 main points. First point is we have to assign the value of a, q, m and counter. This is the first step, and we have to go analyze whether q naught and q minus 1 values are 0 0 0 1 1 0 and 1 1. So based upon those values, we are going to just at the third step we are going to perform the corresponding operations, that is a tends to a plus m or a tends to a minus m, or just we have to shift the register of a, q and q minus m. After finally we have to just go through and check whether the count value is decremented. While the finally when the count value is equal to 0, then we will be getting the final answer. So when the count value is not equal to 0, we have to do the same procedure until we are getting the count value as 0. Okay, this is one of the best technique for doing multiplication for smaller number of integer values, whether it is a signed integer or unsigned integer, that doesn't matter. So just we are going to implement this following 4 steps as you see in this flow chart. These 4 steps you have to remember, and you have to make the implementation of these 4 steps until you get the final count value as 0. Okay, so when the count value is 0, we will definitely get the product of the given multiplicand and the multiplier. Okay, so thank you for listening. So until this we have seen about the normal binary multiplication procedure by using the Booth multiplication algorithm. Okay, so in the next upcoming sessions we will see about various different types of multiplication algorithms. So the multiplication algorithm is very simple, and so much of mathematicians have given different types of solving this binary multiplication. This is one of this Booth multiplication is one of those procedures. There are a lot more procedures available, particularly when we are dealing with arithmetic operations in computer architecture. Okay, so in the upcoming sessions we will be reviewing and we will be solving those kind of arithmetic procedures for multiplication, followed by division also. Okay, so until that, thank you for listening. Keep in touch with this series of computer architecture. So thank you one and all.